So welcome back to day 2. I hope you all are ready for the ice storm coming in. Hopefully it's not as bad as they're saying, but I think from what I've been watching, we're kind of in the brunt of it. So hope you have backup options for warmth if it gets without power. Stay safe. If we don't have class, if we don't have campus open next week, if I have power and internet, I will be having Zoom sessions for the course. If I am out, then the lecture videos are in the course, so you can watch those older ones. So they're all there if you have power and internet. So hopefully everything stays together. So hopefully you've got LogicWorks installed and you worked on Lab 1. Just as you're getting to it, if you get to Lab 3, there is one instruction where the number for the circuit it says to put on there is different than what it is in the picture. The picture is correct. Okay, it's a copy and paste error, I think, when they made that document. So if there's a discrepancy between the text and the image is correct for the circuit you want to put in there. All right, so be working on those. I got the first few labs already graded for those who turned in yesterday. If this is a repeat for you, since basically everything's going to be the same except for the final, it can be tempting not to redo some of these. But I think redoing them will be very helpful to you, just to make sure you understand it. So maybe not the initial labs here, but once we start building circuits, if this is your second time around, I would strongly suggest just starting from scratch. Okay, just to make sure, to reinforce that, to make sure you get it this time. All right, so let's jump into this. Again, the lectures for this course are only going to be about 20, 30 minutes most days, and the rest of the time will be spent working on our labs, and I'll be here to help. And these first 2 weeks, we're not going to be building any circuits. We're just going to get some background information, and week 3 is when we'll start actually building circuits. So here is what a basic computer looks like. The CPU, the central processing unit, is the brains of the operation. It's what controls everything. It's kind of like the conductor at the symphony. It keeps everything in line. Okay. It executes the programs. It fetches instructions from the main memory. It examines them and then it executes those instructions, one right after the other. Of course, with multiple cores, sometimes it's more than one right after the other. So we're running multiple instructions. But the general idea is it fetches the instructions and runs the instructions. And then there is a bus between all devices, between the CPU, between all the devices on the computer that the data has to cross over. Okay? Lots of things connect to it, but only one thing can write to it at a time. So we'll be talking more about that later in the semester when we start putting these devices on our computer. Okay, the ALU is the arithmetic logic unit. It does all the manipulation of the data. It's called arithmetic logic unit because it has, math operations, addition, subtraction, and then logical operations like ands and ors. It's amazing how much you can do with just those 4 things essentially, because everything in math is basically just addition when it comes down to it. So sometimes there's a lot of addition. All right, so the registers are the memory in the CPU that stores the active data we're actually actively working on. Okay, so we'll be building some of those this semester, but that's where the data is stored that we need to work on it. So it'd be nice if we have a lot of them. But the problem with them is they're fairly expensive. They take up space. So there's all sorts of different considerations. Everything in your computer science degree is all about a balancing act. It's like I can get faster speed, but it'll take more memory. I can have more registers, but the CPU will be more expensive, and it'll be harder to dissipate all that heat, and it'll be a bigger chip that might not fit as well. So we try to be as many registers as possible without pushing that balance off too far in one direction. Because if the data is right there, it's a lot easier to deal with it quickly. Okay? Yeah, and the size of the register, if you ever wonder about why is my computer 32-bit or 64-bit, it's because that's kind of the size of the data the computer wants to work with. So 64-bit computers have 64-bit registers. The bus is usually 64 bits wide. Okay, it likes to deal with 64 bits of information, which is why a lot of programmers will sometimes, when they're programming, they need decimals instead of using a float, which tends to be 32 bits, they'll use a double, which is 64 bits, because the computers are generally happier working with those 64 bits. Yeah, registers are almost always the same size. There's some specialty ones like the program counter and the instruction register, which we'll talk about, which aren't as large. But generally they're the same size, though some of them are reserved for special purposes. They may not be able to be used by a program generally, but they're used to kind of manage the CPU and the transfer of the data. And then our control unit is the part that that it switches things on and off. It decides which operation the ALU is doing. It activates registers, which register we're going to read from, which we're going to write to. It controls everything in it to make sure it's like these are the robots, but they can't do anything until the control unit tells it to do what it needs to do. Okay, it activates the right points at the right time to make sure the instructions are run. Okay, and if we look at our schedule here, you'll see we'll be building these things. They're in the very end of the course. We'll have, here's our ALU we're building, and our control unit down here. Our registers we're actually doing pretty early in goal 6, but we'll be building all those parts for our computer. Oh, I didn't think he'd go away. Our data path. Our data path is the path around the computer that the data has to travel, thus the data path. So normally our data is normally in a register. We won't worry about the memory for now, but it starts out at a register. There's usually a register file, which is a bunch of registers that you can activate certain ones. But the ALU usually has a couple registers attached to it, which is the data that's actively being worked on by the ALU. So the data comes from a register, goes into the ALU. There's usually an output register to store the output, and then that gets either written back to one of the registers or it could be written back to the memory. But the data follows a path as it's being manipulated, as the instruction is being run. Okay, and as I mentioned, the ALU has mathematical operations and Boolean operations, and it tends to have input registers and an output register. Now on our computer, we're really just going to have these A and B registers when we build our computer. We're not going to get as complicated as a real one. We're just going to have a couple registers there and not overcomplicate ours. There's basically then two types of instructions. There's the register to memory instruction, which fetches the memory to the register or takes the data from the register and stores it back into the memory. Okay? We usually keep these separate, like any instruction that goes through the ALU to be manipulated always goes back to a register, never back to memory. Any idea why we would do that? Why would we not have an instruction that goes through the register go to the memory, but instead always go back to the register? Why do we keep these instructions separate? I have my chat open for anybody at home who wants to answer. It's slow. Okay, accessing the memory is slow. So the registers are almost instantaneous, but the memory is about 100 times slower than accessing the register. So it's very, very slow. And so we don't want things held up, data that's being manipulated in the ALU. We don't want that held up by fetching memory data from the memory. So that's done as a separate instruction, because oftentimes whatever process is running is going to have to wait in CPU time quite a lot of time. It's 100 nanoseconds, but that's still a lot of time in CPU time. So those are usually separate instructions than our register-to-register instructions. So those who usually fetch data from a couple registers, manipulate it by the ALU, and then store it back again into the register. And that gives us a cycle of the data. Most computers have multiple ALUs. Usually you have a special one for float, because manipulating floats, decimals, are very different than integers. In fact, I remember our first computer was an Apple IIe, and it couldn't do floats. You actually had to buy a math coprocessor if you wanted decimals. Okay? Sorry, I got a piece of ice. Otherwise, everything was integers. Okay? And because, especially since back then, dealing with floats was costly. It was slow. Computers were slow, and so floats especially were slow and expensive, because you had to have a separate ALU for those and a lot of separate instructions. And so unless you really needed them, you weren't forced to pay for that. Nowadays, it's sped up quite a bit. We usually have a separate ALU for that. And when you take assembly, probably next semester, you'll see where we have the separate instructions for our CPUs, whether it's a float instruction or it's an integer instruction, because they have to do two completely different data paths depending on the type of instruction. In fact, there's usually separate sets of registers for floats versus integers. Where are you going? Yeah. All right, so here's the basic cycle of how an instruction is run in the computer. First, you have to fetch that instruction from the memory into a register. Okay? Our memory holds our instructions and it holds our data. But the CPU doesn't work directly with that. It has to first bring it into a register. That's the memory area where the CPU actually does the work. Okay, then we have a program counter. The program counter's job is to keep track of the memory address of the next instruction. And instructions are sequential in memory. And if you have a 64-bit computer, we need to jump 64 bits to get to the next instruction. Okay, so the program counter counts up. When you fetch the instruction, the program counter counts up, so it's ready to grab the next instruction. Okay, then you have to determine what type of instruction is fetched. Okay, most modern computers, Intel and AMD, these x86 computers have hundreds, if not thousands of instructions. I don't know the exact number. I know you have like your ARM processors, which are in your phones, or in the newer Macs. They have hundreds. They're reduced instruction set computers. So they have smaller instructions and less of them. Allows them to actually do them faster and more efficiently. But they have to be fetched, determine what type of instruction they are, and then if it's in memory, we need to access that memory. And then fetch that, if needed, into a register. So if instruction needs some memory that's not already in a register, it has to go get it. And then it can execute the instruction. Once it's done that, we can go back to step one. Do it all over again. I'll give you a head start on this. So RISC versus CISC. So RISC stands for reduced instruction set, and CISC stands for complex instruction set. So the basic idea is, if I were giving you directions to get somewhere, say I wanted instructions to get to Walmart, I can give you a set of instructions going to Walmart, a set of instructions going to Kroger, a set of instructions going to Target, and I can give you a separate instruction for every location you want to go. Okay, and then if you want to go there, you can just grab those instructions, you have them, boom. Okay, so that's a complex instruction set, where we have a separate instruction for everything we want to do, which worked great at the beginning because there weren't that many. Okay, we didn't have sound cards and 3D graphics cards and all bunch of programs running at the same. We didn't have all those complicated things, all the security issues. So that's why the original, 8086 and those original processors, and even our AMD Intel processors and computers, use a complex instruction set, because everything kind of is built, and even modern computers can run those original 86 instructions. They're still in there somewhere. Okay. Reduced instruction set is like, instead of having a separate instruction for everything, I have an instruction for going forward, I have instruction for turning left, I have instruction for turning right. Now I can get anywhere with those 3 instructions, right? So that's what an RISC instruction set is. Each instruction does less. So to do the same thing as a CISC, I'd have to give you a lot more instructions. So you're like, well, hard coding something in there seems to be a lot better, which was great when things were simple. But as things got more complicated, when the first ARM processor, I watched a video on this a year or so ago, when the first ARM processor was invented, they forgot to hook up the power. And the CPU still ran just based upon the power it got from the sending of the instruction, which is how efficient it was. And that's why phones use these reduced instruction set processors, because they are, in the end, a lot faster. And the circuitry is a lot simpler, because you only need to have hard code a few instructions into it. You don't have to have these hundreds of instructions. You can just do a few. And that's why Macs have gone over to the ARM. In fact, even inside our complex instruction set computers, the AMD and the Intels, they actually have a small RISC core in them just to help with speed and efficiency. So the only reason I think we haven't fully switched over yet is because, well, everything works on CISC. And so we'd have to make a lot of changes. But even with Windows starting to get an ARM or a RISC version, we might see that switch eventually, because it really is a lot more efficient and a lot simpler to make. All right. So here's some, if you're going to design a computer, here's some basic ideas that most modern computers try to keep in mind. We want the instructions directly executed by hardware. What does that mean? Well, some instructions some instructions the operating system sends are actually done by software. It's like, well, it gets broken down into actual instructions to be run by the hardware. They may not always be run by the hardware. It could be a software run that has to break it down simpler. But if it can be run directly by the hardware, it's going to be faster. So we try to make sure that we can run most instructions that we're going to run. If we can do it directly on the hardware, it'll be faster. We want to maximize the rate at which instructions are issued. Notice it doesn't say maximize the rate they're completed. It says maximize the rate they're issued. If we can be doing more instructions at once, we'll be doing better. We want instructions to be easy to decode. So we don't want a long, complicated circuitry to decide what this instruction is. Or a complicated, like those 64 bits we have for our instructions, we don't want like every 2 bits to tell us something different. It's good if we just had usually the instruction, there may be this 13 bits is telling something, these 6 bits are telling something, but we don't want it like every bit is something different. We don't want it complicated to decode. Yeah, and as I mentioned before, the loads and the stores are the only time we should actually access memory. Okay, we don't want access to memory when we're actually executing a different type of instruction. Only specific instructions that load and store. Now we're going to break that rule really bad for our computer because we want to keep it simple. We're actually going to have, load one, and we're going to load a value into our register A, but register B is always going to be grabbing it from memory, because otherwise things get complicated. And we want to provide plenty of registers, because again, if we can keep the data we're going to be using in a while, if we can keep that in a register and we don't have to retrieve that again, our program can be a lot faster. Our execution can be faster. And one way to help get a lot of instructions going at a time is pipelining. Okay, and pipelining is basically, running an instruction is not just one step. It usually takes a lot of steps to run an instruction. And so if we can break that up, if we can break those steps up into discrete things, then we can have a different instruction at every step. It's kind of like if you have a car factory, the old way of doing it is we can't start working on the second car until the first car is completely finished. That wouldn't be very good, would it? If we had to wait. Okay, instead, once one car is past this stage, we can start working on the second car. And so you have like 50 cars being worked on at the same time. So that's what pipelining does. It breaks down the running of the instructions into individual steps so that once the first instruction starts, once I get past step 1, I can start a new instruction. So here's time going by. By the time we get to step 5 here, I have 5 instructions at a time, and that fills up my pipeline. There's 5 things going on at a time. Okay, and then from then on out, we're full. But that comes with an issue, though. What if one of these instructions is deciding on my if statement if it's true or false? Well, I don't know where to go next. Or it's a while loop. I'm deciding whether to loop again or not loop again. Well, I can't know which instruction to put into my pipeline until that Boolean expression is finished and I know whether it evaluates true or false. So what do? Do we just sit around and twiddle our thumbs until that Boolean expression goes through? Can we be more efficient than that? How can we be more efficient than just waiting? Because waiting will be wasting time every time. Is there a way we can only waste time some of the time? Any thoughts? Any ideas? I'm looking at the chat for you all at home too. Guess. It just guesses which way it's going to go. And if it's right, great. We keep on going. If we're wrong, we have to clear out the pipeline and start back at the right instruction. But at least if we guessed right, we've saved some time. And so like for a loop, that's pretty easy. Because which way should I always guess on a loop? True, that I'm going to do the loop again, right? Because then I'm only wrong once. So if I loop 1,000 times and I'm only wrong once, that's pretty good. Okay? And this pipeline prediction is one of the, between increasing the speed and efficiency of cache and having good pipeline prediction, those are the two really the big things that's speeding up CPUs nowadays, since we can't really make them much faster. But making this better is a big issue. In fact, back in olden days, when the Pentium was first coming out, AMD started doing something weird. Instead of putting the number of megahertz their computer, their CPUs could do, they would put in kind of in parentheses and up that number a bit. Because what happened was Intel made this pipeline really big so that they can get a lot more instructions going at once, which allowed them to increase the speed and make it faster. But what that meant was when they were wrong, there were a lot more instructions they had to throw out. And so AMD kept theirs shorter, which meant their speed had to be slower, which meant, but if they made a mistake, there wasn't as much to throw out. So while their megahertz was smaller, they were running just as fast as a faster Intel processor, get as more instructions done. And so their marketing department said, well, we'll just increase our number size to say this is like the Intel's this size or another. Okay? Intel does it a lot, where they do stuff like that just to make their numbers look better. But so do a lot of manufacturers. Yep. So it's always a balancing act. It's not just like, hey, I want a big pipeline, or we got to keep our pipeline small. It's always finding that balance. Okay? Why isn't my arrow working? All right, so our primary memory, which is our RAM sticks, which are getting stupid expensive nowadays thanks to AI. So if you had planned on building a computer, hopefully you already got that built, because it's getting ridiculous. Unfortunately, my son was building one this past fall, and it was just starting. It's like, we're going to grab that right now, just in time before it jumped up. But that RAM stores our program and our data. Everything's stored in ones and zeros, and you'll really feel this when you take assembly next semester. You'll really feel how much everything is just ones and zeros. You realize that everything is just, it's how we interpret those ones and zeros that make it do anything. Okay, so the memory actually uses locations to store multiple bits assigned to one address. So every memory address in a computer is, anybody know how many bits is one memory address represents? 8 bits. And it's still 8 bits. It was 8 bits back when memory was in kilobytes. And it's still 8 bits now. That's in gigabytes. I don't know why they keep it at 8 bits, but I guess it just keeps working. But you can address one byte for memory address, which is why some of you probably won't remember this. Back when we're switching from 32-bit to 64 bits in the times of Windows XP, when you had a 32-bit computer, you could only have 4 gigabytes of RAM. That was the max. You could install more than that, but Windows couldn't access more than 4 gigabytes because, let me get my calculator out here, and let me move this over here. If I take 2 to the 32nd power, I get about 4 billion, which is 4 gigabytes. So it had enough space to store that many addresses because the memory address register was 32 bits. And so it can store up to 4 billion values, which allowed it to access 4 gigabytes worth of memory. Now, will we run out of 64-bit? Well, 2, it doesn't just double it, right? 2 to the 64, we got a while yet. Okay, so there's megabytes, gigabytes, terabytes, petabytes, exabytes. So we got a while before we run out of memory space for our 64-bit computers. But that was one of the bigger pushes to get out of the 32-bit range, is because we couldn't access any more memory. So here's an example. Each of these memories have the same amount of memory. Here's 12 addresses that are each 8 bits. So that's 96 bits worth of memory, right? Here are 8 addresses that are 12 bits. Again, 96 bits worth of memory. And here are 6 addresses with 16 bits. Again, 32 bits worth of memory. 96 bits worth of memory. You might be like, well, this seems better. I could have stored a lot more than 4 gigabytes of memory in a 32-bit computer if I did something like this, made each memory address be 16 bits. But there's always a trade-off. What if your data was true or false? Well, that only needs 1 bit to store it, right? But you can only store that in 16 bits, so you're wasting 15 bits. Okay? Whereas here, I'm only wasting 7 bits if I need to store a value that only needs 1 bit. So I'm still a bit surprised that we're still at 8 bits. There's probably a good reason. I'm not sure of the reason, probably just because it's backwards compatible that way. But we're still at 8 bits for a memory address. Well, it probably also has to do with the fact that we have 64 bits to store it now, so we're not going to run out of space anytime soon. So why change it, right? If we have exabytes, if we can have exabytes of memory in our computers, we probably don't need to change it. So that's what we use. Byte ordering. Okay? When we write, which way do we write? From left to right or right to left?
Left to right.
Left to right. All right, so is that done the same way all over the world? No.
Chinese is right to left.
Yeah, and I think the older Chinese is top to bottom.
I mean, I read the more modern one.
Yeah. So is there any good reason why we do left to right?
Because
Yeah, right-handed. It helps because if you're writing, you won't smear. All the lefties know that if you smear the ink if you're going from right to left with your left to right with your left hand. So we went from left to right, we'd be smearing the ink, especially back when it was a little more smudgy, the ink was. So going left to right just made it a little less smudgy. We wouldn't be smearing ink as we were writing. Okay? But with computers, they don't have to worry about smudging the ink. So how are we going to write the data? Okay? And when I say there's not really technically a left to right, it's more like, is the first bit in the data, is that the small value or is that the big value? So if I have, what number is that? Well, it's 1,234, right? But I could write it this way. So when I'm looking at, if the bits are flowing to me and the first number I get is a 1, is that 1 meaning it's 1,000, or is that 1 because it's a 1 bit? It's a 1 in the ones place. Okay, so for computers, it doesn't really matter. It's kind of like driving on the left and right side of the road. If you're in Britain or any of the more modern British colonies, that used to be a British colony that America got out before we really decided, they tend to drive on the left side of the road. I only figured out recently that those who drive on the left side are because they used to be British colonies. I didn't realize that until recently. But everybody else drives on the right side of the road. There's no really good reason on that one, unlike handwriting, which one we picked, but we just picked one. Okay? Probably. So there is no good reason. There may not be. There may be a reason why you do it a certain way. It may work better for the computer you're trying to build or the circuitry that you have to do it one way or the other. So when computers were isolated and didn't talk to each other, it didn't really matter, right? If you're just one computer, whether this first bit of data that came out, whether that was a thousands place or the ones place, as long as everything in your system read it the same, it was fine. The problem started happening when we started networking computers. So when you're receiving a bunch of ones and zeros from a computer, which spot was that 1 and 0? Was that the first? Was that the biggest, the big value, or was it a little value? Okay, and so they started calling that either big Indian or little Indian, and that's Indian with an E, meaning the end. Okay, and that came from Gulliver's Travels. Anybody ever heard the story of Gulliver's Travels? So Gulliver got lost at sea, and he ended up on the island of Lilliputians, which are really small people. They captured him, tied him up, but there were some Lilliputians had a big argument. When you eat an egg, should you start at the big end or the little end of the egg? And if you said you should start at the big end, you were a big Indian. And if you said you start at the little end, you were a little Indian. So computer scientists took that clever idea and decided that's what we're going to use for which side do we start on. Okay? So if I'm laying this data out in memory, the first byte I get from memory, is it this value or is it this value? So like we have a 32-bit word, so these 32 bits, 4 bytes each. If I grab these 32 bits, is the first value stored, is that the smallest value or is that the larger value? Which place value is it? And I'm not, I didn't clear it off. Got to clear it first before I move on. There we go. Okay, so for example, if I had the name Jim Smith, in Big Indian it would look like this. Okay, then the value on the left is basically our biggest value, our biggest place value. It's if we were to write it out, it'd be the spot that's further to the left in Big Indian. A Little Indian, the first value here is actually the one that's on the furthest to the right, if you were to write it out. So if you were to transfer this from a Big Indian computer to a Little Indian computer, and they were spelled out, it would be Midge Tims. Okay, instead of Tim Smith. So you have to, if you were to transfer between those two types of computers, you have to swap the values as you're doing it. You'd have to know, hey, I'm going to send you this data, but I'm Big Indian. And the other computer's like, oh, well, I'm Little Indian, so I'll swap it as I come in to make sure it stays correct for me. All right, cache. Not like the stuff you buy stuff with. This is like a treasure cache, which is just a place that you stash something away, okay, to use for later, generally speaking. As I mentioned before, memory is slow. It's very slow. I mean, it'd be like, you may order Uber Eats from the restaurant that's going to take 15 minutes to get here, but you're not going to order it from some St. Louis and have it delivered. But that would be like waiting for the memory, waiting for a food delivery from St. Louis. It's going to take a while. So we need a way to speed that up. And usually the way to speed things up is to make it more complicated. So again, there's always a trade-off. Okay, but cache is definitely a complication that pays to that trade-off very well. So we have some extra memory here And usually the cache is actually part of the CPU because it has to be close to the cores to where it's going to do the work if it's going to be fast. Because at the speeds we're traveling, just an inch of wire is going to take a lot of time to get data across. Which is why whenever you look at a motherboard, the memory is always right there next to the CPU. You never see the memory down at the bottom well away from it. You really want to shorten that length because the time that electricity takes to travel that wire makes a difference. Okay? And so the cache is usually built into the CPU. And if you look at, I like going to the Newegg just because they display this information nicely for us. If we go to Newegg and we look at CPUs, let's grab some here. So let's look at, if we look at this Intel one, oh, that's okay. Let's look at this Intel one first. And we look specs. Way down here. All right, so right here, it doesn't have an L1 cache. It has an L2 and an L3 cache. We usually have multiple layers of cache in a CPU because, again, trade-offs. Faster caches are usually smaller and closer to the core. But the more cache you have, the more likely the data you want is right there and ready to be used. Okay, so bigger caches mean bigger, faster work. In fact, y'all been paying attention to AMD's 3D cache? So if we look, see if we can find one of those up near the front. Yep, here's one, X3D. So these.
It's shocking how much of a difference it makes.
Yeah. Come on, you. Don't be that way. 128. Remember the other one had like 32? And really the 3D cache is really just the L3 cache. You see, this AMD tend to have 3 levels of cache, with the L1 being very small. It's barely over a megabyte. And this one is still pretty big. A lot of them are like 640 kilobytes or something. L2 cache is a little bigger, but the L3 cache is a lot bigger. And that's especially good for data-hungry things like video games, which is why a lot of video game players like these 3D ones. But if you want to even have more fun, have you all heard of the Threadripper processors? Yeah, I know.
Never used one.
So here we go, Threadripper. So Threadripper is interesting how it came about because it was never on the plans for AMD to build these processors. But a bunch of the CPU designers said, hey, if we were to build a processor that was like, this is our dream processor, this is what we do it. Can we do it? And AMD said, sure, go for it.
It's just upclocked versions of their server ones, right?
Well, it also has 64 cores. Yeah, so this one has 64 cores. And not only that, most motherboards only have 4 slots for memory. This has 8, so a lot more memory. But then you start the cache. It's got 256 megabytes of L3 cache, and it's got 4 megabytes of the L1 cache, which is the really fast cache. Because usually L1 cache is per core. Each core gets its own L1 cache. So divide that up by 64 cores, and they get about average what everybody else gets. And the L2 cache is usually shared amongst a group of cores, and the L3 cache is usually for the whole processor. Okay, but yeah, 8 memory channels. Boy can dream. I mean, there's no way justify, even if I had the money to throw around, it's just like I would never use that many cores. It's really good for like if you're doing video processing or a lot of things like that could use all those cores, but most of us will never have that need. Yeah, this is the big one. That one has 96 cores in it, as opposed to the measly 64 cores. Yeah. Yep. Okay, let's go away from that before I get sad. Anyway, but cache is important. And as I mentioned before, the 2 main things, when you can't increase the core size too much, a number of cores, and you can't increase the speed, it's really the cache and the pipelining that really makes the difference between generations. Making sure having good algorithms for for being able to predict what should go in the pipeline, and also being able to make good predictions of what should be in the cache and which level of cache. All right, so we talked about a few levels of memory. So this is kind of the hierarchy. Registers, as we mentioned, are right there. That's the data that's actively being used. Then we have our cache and our main memory. And then we have our hard drives. Because what's the problem with these top three memories? The volatile, which means that when the power goes out, they're gone. So we need a way to store that for when the power goes out, and that's where our next level is our hard drives, whether you have a spinning rust drives. You know, the older hard drives have the spinning platters or just rust. And they use magnets, so the iron and the rust, they use magnets to flip that positive or negatively charged. But they're just plastic layered in rust. I'm not sure if they use plastic for the, probably don't use plastic. But it's just layered rust that they just do a positive negative charge. And those positive and negative charges are so small now that they actually have to heat the platter. The heads actually heat the platter to expand it a little bit in order to read and write the data as it's passing under the head. It's pretty crazy. Y'all should look at, it's crazy how they can get 32 terabytes on these magnetic drives at just getting that signal, that positive negative charge so small. But then we have our solid state drives, which work a lot like the main memory, but slower. And the reason they're slower is because they keep it around after the power goes off. Although there is some memory now that's actually in production. I think mostly, I don't think it's ready. I don't think they have it for consumer, but for industrial purposes, they have memory that is non-volatile, RAM that's non-volatile. So that I think eventually these two will merge and you'll never have to load data from a hard drive at some point soon. And then tape and optical discs are really cheap for storage, but they're also very, very slow. Tape reading and writing is actually pretty fast. It's fast as these, but finding it is slow because you have to wind the tape to the point in it. That's very slow. So usually just use for backup because it's very cheap per gigabyte or terabyte or whatever to store it. So a lot of companies still use tape for backup. Optical discs aren't used much anymore. That's it for today. All right, y'all, so that's what I have for today. You have about 30 minutes left. So if you've got lab 1 done, great. Again, this is the time to get ahead, so feel free to get labs 2 and 3 done. And I'll be here if you have any help, need any help. Otherwise, I'll stay warm, stay safe. I might see you on Tuesday. I mentioned this earlier before everyone was here. If we don't have class next week because of the weather, if I have power and internet, we'll do just purely via Zoom if the campus closed down. If I don't have power or internet, then on the schedule, you can just watch the previous semester's videos for next week, if you have power and internet. So there's nothing absolutely due next week, so if it takes a week before you get power back, you'll still have time to get everything done. So another good reason to try and get next week's stuff done now. All right, thank you all.